Okay, in this section of the video, we will continue the engineering applications of integrals to calculate the hydrostatic pressure and force, especially the pressure and maybe force on a vertical surface. Okay, so let's say you are given a fluid. Okay, so this is a surface of the fluid and the area A here. So it is easy to find the pressure and force of fluid acting on a horizontally uniform surface. Okay, so let's say you consider the diagram shown here. The force exerted by the fluid with the density rho, okay, not P, so it's to be rho, at a height or depth D on the horizontal surface, you know that pressure equals to rho G H. Okay? In this case, the H height is D, okay, rho G D. So the force is pressure times area, so you get rho G A D. Okay. Well, this is just M equals to rho V. And yeah, the pressure can be found using this formula. Basically, this is just basic hydrostatic pressure, rho GH or rho GD. And Pascal's principles of hydrostatic pressure mention that at any point in a liquid, the pressure is the same in all directions. So if you are standing here at this point here, versus your friend standing at this point here, both of you will experience the same pressure. So in the notes there was a mention that for a diver in the sea, the pressure on the nose is the same with the pressure in both of the ears because they lie on the same horizontal line. So it's quite straightforward to find the pressure and force of a fluid acting on a horizontally uniform surface. But what about vertical surface? So what about the pressure and force acting upon a vertical surface, for example, a wall or a dam? So I took this picture from Google image. So it's easy to find the pressure acting, as a function of height, of a depth of the fluid. But then how do we find the pressure acting on the vertical surface? So more schematic diagram of this dam is, you can see the figure below. So this is the dam, the width and the height, and this is the force acting on the dam surface. It is not a straightforward problem because the pressure is not constant, but it increases as the depth increases. Like previously we say that if you are at this point, it would be the same with you will experience the same pressure as someone who are at this point, because as long as you are on the same horizontal line with the same height, then you will experience the same pressure. But for vertical force, the pressure here is not the same with the pressure here. Okay, the force is not the same. So let's find out how to do that. We cannot just simply add them, because the force, the pressure increases as the depth increases. So the force acting on that surface will be different. So it is best to illustrate the application of integral to calculate the hydrostatic pressure and force by straight away giving an example. So let's say in this case you have a dam with the shape of a trapezoid shown in this figure 9.13, exactly the same example as you're given in the notes. Okay, so the height of the dam is 20 meters and the width is 50 meters at the top and 30 meters at the bottom here. Okay, so you're asked to find the force on the dam due to hydrostatic pressure if the water level is 4 meters from the top of the dam. So 4 meters from the top of the dam. Okay, so let's illustrate the system. You have a water, the dam, and all the measurement. So we illustrate it as a vertical x-axis here with the origin at the surface of the water. So at the surface of the water, x is equal to 0. And then it goes all the way to 16 because the balance is 0 to 16. Okay, so the 4 here, so this is -4 because there's no water. So yeah, okay, because the origin is 0 at the surface of the water. So we label it this way, and then because the width at the top is 50, so if we divide it symmetrically, so you will have here 25 and 25, and at the bottom here the width is 30, so you divide, you have 15 and 15, and then to just help us to go down the dam, so we have this dashed line here, and the width of this width will change as you go down the dam, right? So we put it as A at a specific point in the dam for now. So if we divide it 15 here, then we got this 10 at this side. Okay, so what's next? So if you read the notes, it says that the depth of the water is 16 meters. So you divide the interval. The interval is from x equal to 0 to 16 into n sub-intervals of equal length. And we just choose a random point in the dam xi. So xi, and then it should be xi minus 1. And in the middle here is xi star. Okay, so xi star lies between xi minus 1 and xi. So here the i's horizontal strip of the dam is approximated to be a rectangle where it has the depth delta x, the height or depth is delta x, and the width here is wi, the width of the I horizontal strip. Okay, so how do we find the width? The width changes as you go from this point to this point, the width changes. So we need to put something in terms of another variable. So that's why we have this A here. So if we take out this part of the trapezoid here and we do a comparison with a similar triangle, so you can get the ratio of A over 16 minus xi star equal to 10 over 2 or just 10 over 20 or just 1 over 2, and then you get A equals to 16 minus xi star over 2 or 8 minus xi star over 2. Okay, and the width of the strip I, wi, is equal to 2 times 15 plus A. I mean, the width from this point to this point is 2 times 15 plus A, and equal to 2 times 15 plus 8 minus xi squared over 2 equal to 46 minus xi star. Okay, so this is the width as it goes along the x-axis, the vertical x-axis. And for the I strip, the area of the I strip is equal to just the width times the height, i.e. wi times the height delta x. So that will be equal to 46 minus xi star from here times delta x. Okay, so let's say if you divide the intervals between 0 and 16 to very small section, then if delta x is very small enough such that the pressure acting on the surface on the strip I equal to 1000 times G times xi star. Just the rho G H thing. So rho is the density of water, G is the gravitational force, and gravitational acceleration, and height is the depth. So the depth is xi star. So I is so small such that you can approximate the pressure acting on the vertical surface to be equal to 1000 times G times xi star. So that is for pressure, but we want to find the force acting. So force equals to pressure times area. So force acting on the I strip equals to pressure acting on the I strip times the area of I strip. That will be 1000 times G times xi, and the area is 46 minus xi star times delta x. So, and then of course this is for just one strip, but if we want to find out the total pressure acting upon the vertical surface from 0 to 16, so we have to add them up. So taking the limit from as n approaches infinity, pi ai, and just put in the expression that we got just now and convert it into integral form from 0 to 16 times 1000. I think by this point of time we can just substitute g with 9.8, xi, just x, okay, no more I now, 46 minus x dx. So it looks familiar and you can already integrate this. So you get 9,800 integrate 0 to 16, 46x minus x squared with respect to x. Then should be straightforward from now. And put in the limits. Then you get about 4432213 newtons. So just put it as 4.43 times 10 to the power of 7 newtons. Yep, that's it.